Hi there, this is Stein, University of Illinois. I'm going to talk about heat damage of soybean meal. Soybean products have to be heat processed because soybean meal, as other soybean products, they contain trypsin inhibitors. And trypsin inhibitors, they will reduce the digestibility of all amino acids in soybean meal. And that is a major problem if raw soybeans are used in the feeding of pigs or poultry. To determine the digestibility of amino acids in pigs, we usually determine the ileal amino acid digestibility using a cannula that is inserted into the distal ileum of pigs. A similar procedure is used in poultry, except that we don't insert a cannula. Instead, we sacrifice the chicks and then we squeeze out the digester from the terminal ileum of the chickens. Here's an experiment where we determined the digestibility of amino acids in raw soybeans and in heated soybeans, and we also compared to soybean meal. And we have the raw soybeans in the light blue bars here, the heated soybeans in the dark blue bars, and the soybean meal in the orange bars. As we can tell, the raw soybeans had a digestibility of lysine, methionine, threonine, and tryptophan that was much less than of the heated soybeans and of the soybean meal. However, we can also tell as we heated the soybeans, we got the same digestibility in soybeans as we had in soybean meal. This clearly illustrates why we have to heat the soybean products, because if we feed raw soybeans, we have low digestibility of all amino acids because of the trypsin inhibitors in the soybeans. But when we heat them, we can inactivate those trypsin inhibitors and therefore we get improved digestibility of amino acids. A similar observation has been made in broiler chickens, where chickens were fed raw soybeans. Those are the light blue bars. They were fed soybeans that were autoclaved for 9 minutes in the dark blue bars, or they were fed soybeans that were autoclaved for 18 minutes in the orange bars. And again, we can tell as before that by feeding raw soybeans that have not been heat treated, we have relatively low digestibility of all amino acids. However, as we heat treat these soybeans, we see an increased digestibility in these broiler chicks of amino acids, and in this case, we can see we needed to autoclave the soybeans for at least 18 minutes to inactivate the trypsin inhibitors. This is also illustrated in the weight gain of chickens. Here's an experiment by Batal and others from 2000, where they fed raw soybeans to chickens and compared that to performance of chickens that were fed soybeans that were autoclaved for 3, 6, 9, 12, 15, or 18 minutes. And there was also one group of chickens who were fed a diet containing soybean meal. And we can see here again, as the time of autoclaving increases from 0 to 18 minutes, the average weight gain of these chickens increased linearly. And the chickens that were fed soybeans that have been autoclaved for 18 minutes had performance that was very similar to the chickens who were fed the soybean meal. So again, heating of soybeans is necessary to inactivate the trypsin inhibitors. To determine if a certain batch of soybean meal has been correctly heated, we can determine the urease index, or we can simply measure the quantities of trypsin inhibitors that are left in the soybean meal. If we determine the urease index, we should see a value between 0.05 and 0.20, and these values refer to the increase in pH that is observed in these soybean meals. We don't necessarily need to be down to 0, but we should not be greater than 0.20. If we determine the trypsin inhibitor concentrations, then we should have a value that is less than 4 milligrams per kilogram. Again, we don't necessarily need to be at 0 milligrams because that could indicate overheating, but we should not be at greater quantities than 4 milligrams per kilogram. So what we've seen is that heating of soybean products is necessary. However, if we heat too much, then we get the soybean products overheated, and that is also a problem. We can see that here in this slide, where we see quality of soybean meal is increased as we heat the soybean meal as we've just seen before, but if we overheat it, then the quality will start to be reduced again. So we have to find the medium heating process that inactivates all the trypsin inhibitors but does not result in overheating of the soybeans. The reason overheating is a problem is that overheating will initiate a chemical reaction known as a Maillard reaction. And the Maillard reaction starts when the amino group of an amino acid is condensed with a reducing sugar. And the amino acid that is most susceptible to the Maillard reaction is lysine, because the epsilon amino group of the side chain of lysine is always free and not connected to other amino acids. And what happens is that this amino group of lysine will form a shift base with the reducing sugar, and if heating continues, then the shift bases will be turned into amadoric compounds, and if we continue to heat, then the amadoric compounds will be turned into melanoidins. And melanoidins are cyclic compounds that are brown in color, and they are completely destroyed lysine. And the reason this lysine is destroyed is that the reducing sugar attaches to the nitrogen in the epsilon amino group of the lysine side chain, and by attaching to this nitrogen, the lysine becomes unreactive, meaning it cannot be used in protein synthesis. The amadoric compounds are intermediates in this process, and some of the amadoric compounds will result in reduced lysine digestibility, and some of the amadoric compounds will result in reduced lysine concentration in the product. The melanoidins, as I said before, they are completely destroyed lysine, so the more melanoidins we have, the less lysine we have in the soybean meal, and therefore we will determine a reduced concentration of lysine. So we can see here that heat-damaged soybean meal will have a reduced lysine digestibility, and it will also have a reduced lysine concentration, and those two things always go together. Here's an experiment where we heat-treated soybean meal. We had one batch of soybean meal that we separated into 4 different sub-batches. One of the batches we didn't further heat treat, so that was our control. Then we had one batch that we autoclaved at 125 degrees Celsius for 15 minutes. We had another batch that we autoclaved at 125 degrees Celsius for 30 minutes. And the last batch was oven-dried at 125 degrees Celsius for 30 minutes also. And we can see here that there's a color change in the 2 autoclaved samples. And we determined the color as L star values, and L star means lightness. And we can see that the L star value was reduced as we autoclaved the soybean meal for 15 minutes or 30 minutes compared with the control. However, the oven-dried soybean meal had an L star value that was similar to that of the control. That tells us that the type of heat influences heat damage. In this case, oven drying did not damage the soybean meal in terms of turning it brown, whereas autoclaving, where we have a lot of moisture along with the heat and also pressure, that resulted in a browning reaction of the soybean meal. And the browning reaction was also determined by the A star value, and A star determines the redness of the soybean meal, and we can see an increased redness as we have autoclaved the soybean meal. But again, the oven-dried soybean meal was not more red than the controlled soybean meal. So again, we saw the same thing as with the lightness, that oven drying did not change the color of the soybean meal, but autoclaving did. We took these samples of soybean meal and fed them to growing pigs and determined the digestibility of lysine. And in this slide, we just have the control and the 2 autoclaved samples, and we can see there's a linear reduction in the digestibility of lysine as we increased the time of autoclaving of these soybean meal samples. So clearly we had destroyed some of the lysine, and therefore we saw a reduction in digestibility. We also determined the crude protein concentration in these different samples, and we can see here that there was no change in the total amount of crude protein that we analyzed in the samples. However, when we analyzed lysine, we saw a reduction in the 2 autoclaved samples. We had 3.05% in the control sample, we had 283 in the soybean meal that was autoclaved for 15 minutes, and we had only 2.69% in the soybean meal that was autoclaved for 30 minutes. However, the oven-dried soybean meal contained 3.07% lysine, so that was similar to the control. We also calculated the lysine as a percentage of crude protein. We can see here the control had 6.29% lysine to crude protein ratio. The soybean meal that was autoclaved for 15 minutes had 5.75. The soybean meal that was autoclaved for 30 minutes had 5.57, and the oven-dried soybean meal had 6.25%. And the reason we see this change in the lysine to crude protein ratio is that, as we can see here, crude protein did not change, but lysine concentration was reduced. And if lysine goes down and crude protein does not change, then we will see a reduction in the lysine to crude protein ratio. So we've seen here that heat damage of soybean meal results in reduced digestibility and reduced concentration of lysine, but also in a reduced lysine to crude protein ratio. In general, most crushing plants in the United States, they are doing a good job of avoiding heat damage when they process soybean meal. But there are examples of crushing plants, in particular overseas, where we get soybean meal that is heat damaged. Another example of heat damaged soybean meal is sometimes seen in fermented soybean meal. Soybean meal is sometimes fermented because fermentation eliminates the oligosaccharides, and therefore we can use fermented soybean meal in diets fed to young pigs and young chickens. And we can see here that fermentation in two different sources of soybean meal results in reduction of sucrose, stachyose, and raffinose. And in fact, sucrose is completely eliminated by fermentation, and stachyose and raffinose are either completely eliminated or almost completely eliminated. So fermented soybean meal can easily be used in diets fed to young pigs because pigs don't tolerate the oligosaccharides very well, but by fermenting the soybean meal, we eliminate these oligosaccharides. However, after soybean meal has been fermented, it needs to be dried. So that means that when we ferment soybean meal, we are applying a second drying procedure to the soybean meal. And sometimes that drying procedure results in heat damage to the soybean meal. And here we have an example of 4 different sources of fermented soybean meal. You can see the crude protein varies from 53.2% up to 58.1%. And we also had soybean meal included in this experiment with 49.9% crude protein. The lysine was 3.28 in fermented soybean meal A, 3.16% in fermented soybean meal B, 3.66 in fermented soybean meal C, and 3.46% in fermented soybean meal D. And the conventional soybean meal had 3.17% lysine. We determined the digestibility of lysine in these 4 sources of fermented soybean meal and the conventional soybean meal. And the standardized ileal digestibility was 78.8, 82.9, 88.6, and 89.0% in the 4 fermented soybean meals and 87.0% in the conventional soybean meal. So we can see here that in particular fermented soybean meal A and B had relatively low digestibility of lysine compared with fermented soybean meal C and D and the conventional soybean meal. If we looked at the lysine to crude protein ratio in these sources, we saw that fermented soybean meal A and B had lysine to crude protein ratios of 5.70 and 5.94, whereas fermented soybean meal C and D had lysine to crude protein ratios of 6.30 and 6.08% respectively, and the conventional soybean meal had a lysine to crude protein ratio of 6.34. So as we saw before, if the lysine to crude protein ratio is less than 6.0, then we usually see a reduction in the digestibility of lysine, and that's exactly what we can see here, where fermented soybean meal A and B have low lysine to crude protein ratios and also low digestibility of lysine. We also determined the trypsin inhibitor concentration in these samples, and we can see here that the conventional soybean meal had 7.80 milligrams of trypsin inhibitors, and that's more than the 4.0 milligrams that we usually recommend, and that is likely the reason why the digestibility of lysine in the conventional soybean meal was slightly less than in the fermented soybean meals C and D. Fermented soybean meal C and D contained 1.01 and 1.80 milligrams of trypsin inhibitors, respectively, and that is in the range of 0 to 4 milligrams as we recommended before, and those are the samples with the greatest digestibility of lysine also. We can see that fermented soybean meal A and B contained no trypsin inhibitors, and that is another indication that they were overheated because all the trypsin inhibitors had been destroyed, which in itself is a good thing. However, the excessive heating also destroyed some of the lysine. So this again illustrates that applying heat to soybean meal should be done in moderation so that we can get the trypsin inhibitors destroyed, but without destroying any of the lysine. We have looked at the impact of overheating on digestibility of lysine. Now we'll take a look at some of the practical impacts of heat damage when we feed pigs or broiler chickens. Here's an experiment where we started out with a source of soybean meal. We then heat damaged the soybean meal by autoclaving it at 130 degrees Celsius for 60 minutes. And we can see that resulted in a browner product than what we started out with. And we heat damaged it in 2 kilogram batches. We then used either the controlled soybean meal or the heat damaged soybean meal and mixed diets fed to weaning pigs. We can clearly see the change in color here as we heat damage the soybean meal, and we can also see that the L-star value or the lightness was reduced in the heat damaged soybean meal. We can see the crude protein was not much changed, but lysine was reduced from 2.91 to 2.51%. And the lysine to crude protein ratio here was 6.1 in the controlled soybean meal and 5.4 in the heat damaged soybean meal. So again, based on what we saw before, we would assume that pigs fed the controlled soybean meal with a lysine to crude protein ratio of 6.1 would perform well, but clearly the autoclaved soybean meal with a lysine to crude protein ratio of 5.4 is heat damaged. We mixed these two sources of soybean meal into two different diets and fed it to weanling pigs, and we can see here that pigs fed the controlled soybean meal had an average daily gain of 490 grams per day, whereas pigs fed the heat damaged soybean meal only gained 351 grams per day, so almost a 140 gram reduction in average daily gain as we fed the heat damaged soybean meal. The final body weight of the pigs was 20.7 kilograms for the pigs fed the controlled soybean meal and 18.0 kilograms for the pigs fed the autoclaved soybean meal. The gain to feed ratio was 0.49 and 0.35 for pigs fed the control and the autoclaved soybean meals, respectively. We also determined the plasma urea nitrogen, and we can see an increase in plasma urea nitrogen as we fed the autoclaved soybean meals, indicating that these pigs have reduced protein synthesis and therefore had more nitrogen in the bloodstream, which was turned into urea. So instead of synthesizing protein, they excreted the nitrogen in the form of urea. So combined, these results clearly indicate reduced performance and increased plasma urea nitrogen of pigs fed the overheated soybean meal. So this is a real practical result that can be observed if soybean meal that has been overheated is used in diets mixed for weaning pigs. A similar experiment was conducted with broiler chickens, and here again we had two sources of soybean meal, one that was not heated and one that was autoclaved. You can see here the crude protein was exactly the same in the two sources as we would expect, but lysine was reduced from 2.84 to 2.60, and that resulted in a reduction of the lysine to crude protein ratio from 6.0 to 5.5. Again, the two sources of soybean meal was used in diet formulations, and then the diets were fed to broiler chickens. The body weight gain from day 10 to day 28 post-hatch when the chicks were fed these diets was 1,690 grams for chicks fed the controlled soybean meal, but only 1,480 grams for chicks fed the heated soybean meal. So again, we saw a clear reduction in body weight gain as the heated soybean meal was used in diet formulation. The gain-to-feed ratio was also reduced from 0.66 in the chickens fed the controlled soybean meal to 0.62 in the chickens fed the heated soybean meal. So exactly the same way as we saw with the pigs, there's a reduction in performance of chickens as we use heat-damaged soybean meal. So we have now seen the negative effects of feeding heat-damaged soybean meal to both pigs and broiler chickens. From a practical perspective, it therefore becomes a question: how can we determine if a particular source of soybean meal is heat damaged? We have already talked about determining the lysine to crude protein ratio, but we can also look at other measures of heat damage in soybean meal. One of the ways to assess heat damage in a certain batch of soybean meal is to determine what we call the reactive lysine. And the reactive lysine is determined as the amount of lysine that can be used for protein synthesis. As we've seen before, heating of soybean meal will result in some lysine that is not heat damaged, but some lysine that is heat damaged, and we call that unreactive lysine. When we start amino acid analysis, the first step is to acid hydrolyze the proteins. And acid hydrolysis of unreactive lysine will result in 3 separate fractions. One of the fractions is regenerated lysine. One fraction is turned into furosin, and one fraction is turned into pyridosine. Furosin and pyridosine are 2 specific amino acids that are synthesized during acid hydrolysis, whereas the regenerated lysine looks like normal lysine. When we analyze the lysine, the regenerated lysine will appear in the peak for analyzed lysine along with all the reactive lysine. So when we see the peak for analyzed lysine, we don't know how much of that was actually unreactive lysine and how much was reactive lysine. We can, however, include a standard for furosin in the analysis also, and furosin will then show up as a separate peak in the chromatograph. It is assumed that the 3 fractions for regenerated lysine, furosin, and pyridosine always will have a constant ratio. So 40% will be regenerated lysine, 32% will be furosin, and 28% will be pyridosine. And if that is the case, then by determining the amount of furosin, we can calculate how much regenerated lysine was included in the analyzed lysine peak, and we can then subtract the regenerated lysine from the analyzed lysine and therefore calculate reactive lysine. So this is one way of assessing the heat damage of a particular source of soybean meal. We simply need to analyze the furosin in that sample and then calculate regenerated lysine, subtract that from analyzed lysine, and then we calculate the reactive lysine. If we look at our soybean meal samples that I showed before, where we had autoclaved soybean meal for either 15 or 30 minutes or oven dried it, we can see here that the furosin was also determined, and as the lightness of the soybean meal was reduced in the autoclaved samples and the redness was increased, we also see an increase in the amount of furosin in these samples, which indicates that they were indeed heat damaged. In contrast, the oven-dried soybean meal had a furosin concentration that was similar to that of the control diet, as we also saw before. We have seen several times that heating results in increased redness or in a brown color in soybean meal, and it is therefore easy to determine the color in soybean meal and relate that to heat damage. However, it is not always possible to simply determine the color of a specific source of soybean meal and then predict the digestibility of lysine in that source. As we've seen here, heat damage causes color change, and there is a correlation between color and standardized ileal digestibility of lysine within the same batch of soybean meal. We've seen that several times. However, the measured color is also influenced by moisture in the sample and by particle size, and therefore it is not always possible to get a clear correlation between color and digestibility if we collect different samples of soybean meal, and it is therefore not possible to simply measure the color in soybean meal and from there estimate the digestibility of lysine. So if we use color, it should be used only within the same production facility where particle size and moisture concentrations do not fluctuate, and maybe we can use it if we procure soybean meal from the same supplier and measure color, and we know then if we get an increase in redness or more brown color of the soybean meal, then we can assume it has been heat damaged. But if we collect soybean meal from different suppliers, then it is not possible to use color measurements as an indication of heat damage. A couple of other opportunities for determining overprocessing of soybean meal include determining the KOH protein solubility or the protein solubility index, also called the PDI. Here are results of an experiment in which raw soybeans were fed to broiler chickens. The soybeans were either not heated, that's the light blue bars, they were heated for 12 minutes. In the purple bars, they were heated for 24 minutes. The green bars, they were heated for 36 minutes in the orange bars. And there was also a source of soybean meal included in this experiment, and that's shown in the dark blue bars. You can see the gain, and that's expressed here as percentage of the gain for chickens fed the soybean meal. And as we've seen before, chickens fed the raw soybeans that were not heated, they had a lower gain compared with chickens fed the soybean meal. But as we increased the time of heating of the soybeans, we saw an improved gain of the chickens, and the chickens fed the soybeans that were heated for 36 minutes have gain that was similar to that of chickens fed the soybean meal. We also determined the KOH in these samples of soybeans and soybean meal, and we can see that the KOH solubility was reduced from the raw soybeans to the soybeans that have been heated for 12 minutes and further reduced when soybeans were heated for 24 or 36 minutes. And again, the 36-minute heating resulted in KOH solubility that was similar to that of soybean meal. So the results of the KOH solubility here were similar to that of the gain of the chickens, where the soybeans that were heated for 36 minutes had gain and KOH solubility that was similar to that of soybean meal. The PDI was also determined in this experiment, and again we see a reduction as soybeans were heated, and soybeans heated for 36 minutes had a PDI that was similar to that of soybean meal. So in this case, it looks like both KOH and PDI could be used to predict the degree of heating in these soybeans. If we determine KOH or PDI, we should have a KOH solubility that is in the range of 75 to 82%, and that indicates soybeans that have been probably heated, and the PDI should be in the range of 15 to 30%, which also indicates proper heating of the soybeans. So KOH solubility and PDI, they are used to determine if soybean meal is overprocessed or heat damaged, but they cannot be used to indicate if soybean meal is underprocessed. To conclude on this presentation, we have seen a couple of different ways we can evaluate heat damage in soybean meal. One way of doing it, as we have talked about, is to calculate the lysine to crude protein ratio. If that ratio is greater than 6.0, then we don't have any heat damage in soy protein. However, if it is less than 6.0, then we do have heat damage in soy protein. We can also determine KOH solubility. The KOH solubility should be between 75 and 82%, or we can determine PDI, which should be between 15 and 30%. If we have determined that ingredients are heat damaged, then it may be necessary to reformulate the diets and include more amino acids in the diets to prevent the reduction in productivity that we saw for both pigs and chickens fed heat-damaged soybean meal. The reactive lysine procedure can also be used, however, that requires analytical skills and prediction equations to determine if soybean meal has been heat damaged. Color can be determined, but as we discussed, determination of color is valid only if moisture and particle size are constant, and therefore we can only use color measurements within the same production facility where particle size and moisture do not fluctuate. The lysine to crude protein ratio can always be used as an indicator of heat damage. With that, I want to acknowledge my current group of students and technicians who have helped conduct the research I've discussed here, and there's more information about our work on our website, nutrition.ansci.illinois.edu.